This problem is not particularly special or unique. It's the one that I found because it was easy to find. That said, it's still worth taking a look at briefly to kind of talk about how you would determine which of these differential equations go with these direction fields. And so let me talk about this for a minute because I think it's worthwhile. And let's actually look at this first one here. So let's look at A. We've got dy dx equal to 2 minus y. Y prime equals 2 minus y. When I am trying to figure out which of these direction fields to go with, there's two things I like to look for, at least two. What I really look for first is looking for where this might equal 0. So if I'm going to say, where is this equal to 0? And if I'm talking about where that's equal to 0, that means where all the lines are going to be horizontal, right? Because the derivative is 0, the slope of the tangent line is 0, which means the horizontal line. So if that's going to equal 0, then I'm going to get 2 equal to y, or y equal to 2. So all along the line, y equal to 2, all of my little lines should be horizontal. If I look at, so be careful, that's where 2 is right there. Definitely not there, right? That's not it. 2, nope, definitely not there. That's not it. 2, oh, this one, look. So this one's, oh, sorry, I missed it. The 2 is not there. Sorry. I was assuming it was centered at the origin. It is not. Apologize. Let's go back and look again. There's 2. Okay, that could be it. That doesn't mean it's necessarily. Sorry. Maybe all of these are okay. So these first 3 definitely all could be the first one. Sorry. Apologies. Good lesson to make sure you're reading the graph correctly. I definitely saw that I thought it was -2, -1, 0, 1, 2. Not 0, 1, 2, 3, 4. So it looks like it could be 1, 2, or 3. So we need to do more. So I would also point out that in this one, the derivative of y, or the slope, only depends on the y value. Meaning, if I go up or down, the derivative should change. But if I go left or right, they actually shouldn't. So if I look here, like if I go, for example, that's kind of hard to see actually. So if I pick a particular y value here, well, look, if I go left or right, the slopes do change. If I go left or right, the slopes do change. But here, like at say y equal to 3, going left or right, the slopes don't change. The slopes are totally independent of the x value. So since this differential equation is autonomous, right, it only depends on y, this one must pair with 3. Because that's the only one where if you move left or right, it doesn't affect what the y value, the derivatives are. Cool. But I would say the first thing I look for is the setting it equal to 0. So let's go ahead and look at B. Again, we're going to get the same thing. We're going to do the first same thing here. So if I look at B, which is y prime equal to x times 2 minus y, I'm going to set that equal to 0 because I find that to be helpful. I am going to get y equal to 2. So it could be 1 or 2. It couldn't be 4, right? Because 4 definitely along y equal to 2. Holy smokes. Can I point to the right thing? Man, these are all like, so they're not all the same, which I should have realized from the get-go here. The scaling is not the same, all of them. So y equal to 2 up there, definitely not 0, right? Okay, good God. Y equal to 2 there is 0. This one's out because we already used it. Y equal to 2, not 0. Okay, so here we actually can eliminate all but one of them, right? It's got to be 1 because 1 is the only one where y equal to 2 is still giving you 0. Also, we know that x equal to 0 would also be a line where all the slopey parts are horizontal lines. So, and if you look here, x equal to 0, oh yeah, all of the slopey parts are horizontal lines. So B has to be paired with the first one. But when I'm trying to pair these, sorry, I didn't mean to start there. When I'm trying to pair these, I'm really just looking for where am I getting horizontal directions, I guess is the best way to say it. Maybe the best way to say it. I'm not good at the language is escaping me here. I would probably do the one with sines and cosines last because it looks intimidating. So let's look at C. Also, it's the last letter. So let's look at C here. Y prime equal to x plus y minus 1. Again, I would set that equal to 0. And if I do, I would solve for y. So here I'm going to get y equal to 1 minus x, or negative x plus 1. So I look at the line y equal to negative x plus 1, which has a y-intercept of 1 and an x-intercept of 1. Then that straight line should have all horizontal little tangent lines through it. So let's see. Well, I know it's not 1 or 3, but even though it could have been like, here, right, if I look at the line y equals negative x plus 1, it would look like that. That definitely does not have horizontal lines going through it. Right, I could even draw it here just to kind of show you even better. Right, if I actually draw this line here, that line doesn't have all horizontal lines going through it. If I draw it here, there's my, oops, that's not the right line, James. Oh my gosh, it should have been this one, sorry. Still, that's kind of cool that that's exactly the same amount. Still, right, that line there doesn't have all horizontal lines going through it. Well, let's look at this one here. Nope, definitely not. I know it's not going to be this one, but I'm going to draw it anyway. I can find the right numbers here. Definitely not all horizontal lines. Let's look at this one here. There's my one. There's my one. And even though it might be kind of hard to see it. Ooh, in fact, the graph here might not have come out so perfectly here. It's very hard to see it. I'm having a hard time seeing it. You can kind of see it. You can see, right? Horizontal line there, horizontal line there, horizontal line there. It's a little hard to see because the quality of the graph is maybe not excellent. But you can convince yourself, if you draw your line well enough, that all those are there. You can also start just picking values, right? Like if you're not sure if that's it, you might say, well, okay, y prime is x plus y minus 1. If I pick something like the point 0, 0, then y prime is going to be 0 plus 0 minus 1. And at 0, 0, oh yeah, the slope was negative 1. So that seems right. I usually look for the setting the thing equal to 0 though. And then my process of elimination, although that's kind of a cop-out. By process of elimination, we could say so I should say C is paired with 4. And then we could say that D, which is y prime equal to sine of x times sine of y, is going to be paired with, you know, it has to be 2 because that's the only one left. We should still look at this stuff. So if this was going to equal, again, I'm doing the usual thing I'm going to do. If I set that equal to 0, I know that this is equal to 0 when my angle is like 0 or pi or 2 pi. And if my angle is 0, oh yeah, when it's 0, I'm definitely getting 0. Or when it's pi, there's pi like right about there, right? There's y equal to pi about it there. And down there is y equal to negative pi. And we're also getting it when x is equal to 0 or pi as well, because whether x equals 0 or plus or minus pi, or y equals 0 or plus or minus pi, all of those will make sine equal to 0. So both, so really this line, this line, this line, this line, this line, and this line are all places where the directions are horizontal. So that's what I like to think about when I'm trying to match a direction field to an equation, is set the equation equal to 0 and try to find where that equation equal to 0, what lines or curves make that true. It's a little, I mean, it's a very kind of guess and checky kind of thing. It's not an exact process every time, but it usually works pretty well. All right. Sure. I know a few people some people did ask for a few more first order linear differential equations problems. So let's look at a couple of those. Maybe we'll do one more Euler's formula problem. Yeah, okay. Yeah, all right. One more, another Euler's, and then we'll start talking about vectors, matrices, which you're definitely gonna, so how many of you have to take 17C? Most of you. If you're taking 17C, you definitely, the thing you should remember the most is the vectors and the matrices, a little bit of the differential equation stuff, although not as much, but still, yeah. Because you won't do it at first, but then like once you get to like week 4 or 5, then it's all like matrices and stuff and finding eigenvalues and eigenvectors, which we will talk about this quarter. But let's back it up a little bit. Let's look at these couple of examples. So let's say Sure. Let's say we want to solve the following first order linear differential equation. X cubed y prime equals e to the x to the negative 2 minus 2y. Oh, that looks, can you guys see that okay? Can you? I mean, I can turn off the lights. I mostly don't mind. I don't mind, bro. It feels so dirty. That fine? So I thought. Okay, so for sure not separable. Right? We've got something with x's plus or minus something with y's, not going to happen. So we try to make it look like the usual format or the standard format. So first, we want the y prime and the y on the left. Let's write it as x cubed times y prime plus 2y equal to e to the x to the negative 2. And then we're going to divide everything by x cubed. So then y prime plus 2 divided by x cubed times y equal to 1 over x cubed times e to the x to the negative 2. It looks really gross, which is kind of good news. Usually when you're doing these, if things look gross at this stage, it's because they're probably going to work out not too incredibly terribly. That's not always a guarantee, though. But now we've got the standard format. So I would somehow make it clear to everyone that I know that that's my P of x. And that there is my Q of x. We're going to find our integrating factor. Mu of x is e to the integral of 2 over x cubed. And I definitely should write that as e to the integral of 2x to the negative third to make life easier for myself. So integrating that, I get e to the 2x to the negative 2 divided by negative 2, which is just e to the negative x to the negative 2. A lot of the times you have an e to the natural log or something. We don't have that here. So this is what we got. And then I think it's good practice to multiply it, right? To show all the work. It's good to show all the work, especially if your teacher wants you to show it. So we're going to multiply the whole equation by e to the negative x to the negative 2. So we're going to take this equation written in their standard form and multiply it by e to the negative x to the negative 2. So we're going to have e to the negative x to the negative 2 times y prime plus e to the negative x to the negative 2. I'm going to rewrite 2 over x cubed as 2 times x to the negative third just to make it more obvious what's going on here. Times y equal to 1 over x cubed times e to the x to the negative 2 times e to the negative x to the negative 2. And we should definitely simplify that. That is definitely going to be e to the 0, which is 1. So here's what we've got. All right. Every time when you do this, the left-hand side is the derivative of a product. It's always the case. In this case, the left-hand side is the derivative of, just look at this part here and don't write y prime. Write y. So that's e to the negative x to the negative 2 times y. Derivative of all that is equal to, let's see, if I simplify that, that's just x to the negative third, or 1 over x cubed if you prefer. This is not going to suck. It's great. Now what? What do we do? Why do we do this? We're going to do that in the next step, after the step we're about to do. There's one other thing. We're saying the derivative of this thing here is equal to 1 over x cubed, which means e to the negative x squared times y has to be the antiderivative of 1 over x cubed. And now you're right, Maggie. We're going to divide everything by e to the negative x squared. And we're also going to integrate this. Let's do the division first, though. Let's write it as 1 over, oh, I should write y equals, because that would be correct. Y equals 1 over e to the negative x squared times the integral of x to the negative third. And I would do two things at once here. I would write 1 over e to the negative something as just e to the positive x squared. And the integral of x to the negative third is x to the negative 2 divided by negative 2 plus c. And we definitely need the plus c there. It is vital. And I would leave it like this. That's our solution. Questions about anything we did? All right, let's do one more. So these problems I think are fun personally because, I like math. What can I say? Some people are strange. Some people like math. It's not that strange to like math, but you guys like, sure, James, sure. Let's look at this next one. Let's look at x times y prime. Which way do we want to go here? Plus y is equal to. I want to do that. I want to do that. Let's see which one's going to be. Let me think for a second here. Oh, that'll be interesting. That'll be terrible. Yeah, that. No, that'll be fine. Yeah, sure. Let's do that. Equals x squared natural log of x. All right. I want you all to do the first two things. Step 1, rewrite in standard form. Step 2, find the integrating factor. Find and simplify as much as possible the integrating factor. I'll give you like 3 minutes. Sure. About a minute left. You don't have to stop at step 3. You can keep going if you want to do the rest of it. I was trying to set realistic expectations. Okay, it's been 3 minutes. So to rewrite in the standard format, in this problem, it's always isolating y prime. So you're just doing either multiplying or dividing by whatever you need to get y prime by itself. Here we're going to divide everything by x. Divide by x, and we're going to get y prime plus y divided by x equal to x times natural log of x. This one always so this particular problem bothers me a little bit, and I'll tell you why in a minute. It almost feels like we didn't, so you'll see in a minute, we're going to kind of undo what we just did. So our integrating factor here is e to the integral of 1 over x dx, right? I should point out here, our p of x is 1 over x. And our q of x is x natural log of x. So then e to the integral of 1 over x is e to the natural log of x, which is just x. So we're going to multiply everything by x, which feels like we're exactly undoing what we just did. Oh well, such is life. So if we do that, we have xy prime plus 1 times y equal to x squared times natural log of x. And now the left-hand side is totally the derivative of a product. This is exactly the derivative of x times y. Technically, we didn't need to do all this to get there, but it doesn't usually happen this way, right? It doesn't happen usually that you isolate y prime and then you end up multiplying, and then the integrating factor ends up being exactly the thing you divided everything by. Occasionally it does, usually it doesn't. Feels kind of lame, but well. And then the right-hand side is still x squared times natural log of x. And then we integrate. We say that x times y is equal to the integral of x squared times natural log of x dx. And if you're the kind of person that likes to jump, so technically you could maybe not really get away with writing your answer was 1 over x times the integral of x squared times the natural log of x. But really, we all know better. We know we shouldn't stop there. We know we have to finish this integral. And to do this integral, we have to do integration by parts. So we're going to let u equal. It's always tempting to make the wrong choice here. It's always tempting to make the wrong choice here. U is the natural log of x. Right? Late. L-A-T-E. We pick u equal to a logarithm if we've got one, and we definitely have one. dv is the rest. It is your x squared dx. Sorry, that's a little squished in there. And then du is 1 over x dx. V is the antiderivative of x squared, which is x cubed over 3. So writing this out, we're going to have y equal to 1 over x times uv x cubed over 3 times natural log of x minus the integral of v du x cubed over 3 times 1 over x dx. And the whole point, I know it's been a while since we talked about this, but the whole point of integration by parts is to get a new integral that is easier to integrate. That's actually what we're doing, is we're rewriting this. Yeah, you're getting this UV thing here as well, but the new integral, there is going to be a new integral, and it's supposed to be easier to deal with. And it is easier to deal with. We're going to rewrite this as y equal to 1 over x times x cubed over 3 times the natural log of x minus the integral of, well, let's bring the 1/3 out in front, and x cubed divided by x is x squared. And that is much easier to anti-differentiate. So then finally, we're going to say that y is going to equal 1 over x times x cubed over 3 times natural log of x minus the integral of x squared is again x squared is again x cubed over 3. 1/3 times x cubed over 3 is going to be x cubed over 9 plus c. And then you can leave your answer like this if you like. Or you could distribute the 1 over x and say your answer is x squared over 3 times natural log of x minus x squared over 9 plus c divided by x. That is how I personally like to write it, but either way is fine. All right. First order linear differential equations. We're probably done with them until you have your final exam. They have to imagine there'll probably be one on your final exam. Maybe not. Your teacher might tell you whether or not there's going to be one, but if it were me, I would probably put one on there. Not a super hard one, but I would put it on there. Question, Maggie, or just chilling? Just questions. Process is always the same. It just takes practice. All right, let us look at. Yeah, we'll do one of those. Okay, maybe we'll get to vectors. Okay, so let's look at. Some people ask for something like this. I feel like I'm maybe doing the things people ask for, maybe like a day too late. Sorry if that's the case. Oh no, people fill this out on Saturday. People ask for these things on Saturday. I feel no remorse at all. Not remorse, no regrets. Okay, let's look at the following. We want to, where did I write? I had a good question I wrote down over here. Yeah, let's try this one. Determine the local stability for dy dt equal to y times y minus 6 over y plus 1 squared. Yeah, that seems extra terrible, James. Sure. I should say determine local stability for the equilibria of this differential equation. The equilibria here should be not too terrible to find. In fact, I want you all to find the 2 equilibrium right now. There are exactly 2. There are not 3. There's exactly 2. So, to find the equilibria, just like every other time, we're setting the derivative equal to 0. And to me, it feels obvious what the solutions are here. What's one of the solutions? Yeah, definitely 6. Really, what you can do is you can multiply the top and bottom by the denominator and say we just have y times y minus 6 equal to 0, which means you either get y minus 6 equal to 0, which gives you y equal to 6, or you get y equal to 0, which gives you y equal to 0. X equal to -1 is not an equilibrium here because the derivative would be undefined there, which is definitely not a place where things aren't changing. It's a place where the function's undefined on its own. So certainly not y equal to -1. All right. So let's pretend that someone had asked us to do this and they asked us to do it using the derivative, right? Which is where I don't know if there's actually a good name for that. I just think of it as the derivative method versus the graphical method. Maybe it's actually called the local stability criteria. I feel like either one. But let's pretend someone said do it using the derivative. Okay, wow, someone was not nice. Right? If they said this was a test question, said you determine if these are stable or unstable using the derivative of this thing. What they're really doing here is testing your ability to take a derivative in addition to your understanding of the material. All right, if I had to take the derivative of this, so let's say we've got g of y equal to this thing here, I definitely want to multiply out the top. I want to write it as y squared minus 6y. And I actually don't think I want to multiply at the bottom. I think I want to leave it as y plus 1 squared. Okay, we're going to try and do this with minimal effort. Because really, if you're talking about exams, minimal effort to get the desired result is what you want to do, because you want to save your energy for all the stuff you have to do. So let's find g prime of y. G prime of y is going to be the bottom times the derivative of the top, which is 2y minus 6, minus the top, y squared minus 6y, times the derivative of the bottom, which is not as terrible as it seems. It's 2 times y plus 1 to the first times 1, divided by the denominator square, which is y plus 1 to the fourth. And in my opinion, there is no good reason to simplify this. Because all I'm trying to do is figure out what's happening when I plug in 0, what's happening when I plug in 6. So let's plug in 0 first, because that shouldn't be too terrible. So g prime of 0, I've got 1 times negative 6 minus 0. 0 times I don't care. 0 times anything is 0. All divided by 1 to the fourth power. That's a negative 6. Minus 0 is still negative 6. Divided by 1 is still negative 6. It's negative 6, but I really just care that it's negative. So since g prime of 0 is negative, we know that y equal to 0 is stable or unstable? Dun, dun, dun. Stable. Thank you. Yes. Okay, let's look at the other one, which might be harder to deal with. So let's figure out what's happening at 6. So g prime of 6 is going to be 6 plus 1 squared, which is 7 squared, times 2 times 6 is 12, minus 6 is still 6, minus, if I plug in 6 here, if I remember that this was y times y minus 6, it's still going to give me 0 there. Or you could say 6 squared minus 6 times 6 is 0. So I still get a 0 there. And then the denominator is 6 plus 1 to the fourth. And again, I don't actually care what the value is, but it's certainly a positive number divided by a positive number. That's going to be positive. So we know that y equal to 6 is unstable. If I was asked this question on an exam and for some reason I was not able to compute the derivative because it just seemed like I forgot the quotient rule, forgot to change it, like something wasn't gelling for me. If this was a question on the test and I couldn't do that part, I would do it the graphical way. That's still worth, in my opinion, something. Like, because you're still showing you understand what you're doing and you know how to determine stability and instability. So if you're going to graph this, it's actually not too terrible to graph. Let me just show you really quick. So, or graphically. So I know I've got an intercept at 0 and at 6, and I've got a vertical asymptote at -1. So my graph looks something like, so -1 here. And then I've got an intercept at 0 and at 6. And what I really need to do is just figure out if it's positive or negative in between. So if I pick a number between 0 and 6 and plug it in, like 1 times -5 over 2 squared is a positive times a negative over a positive, which is going to be negative overall. So between 1 and 6, it's going to be negative. And then after 6, it's going to be positive. I don't really know what it's doing. And between -1 and 0, it's also going to be positive. And it probably does something like this over. Oh, it probably actually doesn't. Probably does something like this over here. I don't really care. I don't really care because that part's not important. The only part that's important is what's happening on either side of 0 and either side of 6. And then we have to label this at these axes correctly. This is the y-axis. This is the dy dt axis. I like drawing the arrows. I think it's fun. If dy dt is above the horizontal axis, we are increasing. If dy dt is below the horizontal axis, we are decreasing. If we're above, we're increasing. So graphically, we can also see, oh yeah, y equal to 0 is stable because the arrows are pointing towards it. Y equal to 6 is unstable because the arrows are pointing away from it. I think that is a perfectly reasonable way to answer this question. If it were me, I would ask the question. I would let students kind of do it either. Well, probably not, because grading that seems like a pain in the butt. If I was a nice person that felt like spending all my time grading, I would ask this question either. I'd be like, yeah, they should be able to answer the question whichever way makes more sense, because both ways are totally valid. Yeah, cool. Probably not going to start talking about vectors again. Sorry, I lied. I didn't mean to lie. I just got caught up doing the other stuff. So one more thing, and then if we have time, we'll talk about vectors. We'll have plenty of time to talk about vectors in the coming weeks, so don't feel like you're missing out if we don't get to it today. But let's talk about an Euler's method example, because they're so fun. So let's look at this example. Let's say, and I don't think I've done this example because I just made it up, but you never know. Sometimes I make up examples that are exactly the same because your brain works in certain ways. It's funny looking back at like notes I've written in the past, like I come up with the exact same example totally organically because it just seems like it makes sense. Why wouldn't you use that example? So let's look at this example. Use Euler's method. Ooh, we'll make it, yeah, we're gonna make this one extra fun. Don't worry, it's not gonna be bad. Usually, well, it's not any worse than it would usually be. To estimate y of 2 given that y of 0 is equal to 1 for the differential equation y prime is equal to x plus y minus 1. And then later on we'll solve it, just because why not? It seems like a good problem to solve. So I think we can solve this, yeah. So first and foremost, sorry, with a step of h equal to 0.5. All right, so it's probably worth memorizing this formula, even though I don't like it. I'm going to call this my f of x comma y. And Euler's formula is written in the following way. The next y value is equal to the previous y value plus your step times your derivative at your previous x and y value. The idea being, of course, that if this is your point x sub n comma y sub n, and you're trying to find your next y value, well, you're just taking your previous y value and you're adding on the rise, which is just your slope times your run. And there's your slope. There's your run. There's your previous y. Do you have to remember all this to make the formula work? No. Is it nice to know what you're doing? Of course. All right, so let's do it. Our first y, so I'm going to find, I know that y of 0 is equal to 1. That's a given. You have to have a starting place. And then the next y value is going to be y evaluated at 0.5, right? I'm moving 0.5 over, and I'm going to figure out how much more up I need to go. So that's going to equal my previous y value, y of 0, plus my step size, which is 0.5, multiplied by f of 0, 0. That 0, not 0, 0. I always make that mistake. F of my starting point, which was 0, 1. That's going to be y of 0, which was 1, plus 1/2, or 0.5, and f of 0, 1. And literally to find f of 0, 1, you're just plugging that in to this equation here. So 0 plus 1 minus 1 is 0. So my new y value is 1. paper. So just so you all can see it, because I think it's nice to see it. Here's what we've done so far. We started out. Let's make things real clear here. Yeah, let's make those half values. You don't need this picture. I just want you to see what I'm doing. So I started out here, and at that point, my direction field had a slope of 0. So I just moved a half over in the direction of the slope. So I moved from here to there. Okay, now we're going to find the next one. Don't worry, we'll come back to that picture. So now I'm increasing to the next step over. So y of 1 instead of y of 0.5. And that's going to equal y, the previous y value, plus, again, the same h value there, f of my new xy coordinate. So my new x coordinate, well, I moved 1/2 over, so 0.5. And my new y value is the same as my previous y value. The point here is 0, 1. The point here is 0.5, 1. All right, that's what I'm plugging in. 0.5 for x, 1 for y. And then that's going to equal, well, y of 0.5 is that value there. And f of 0.5, 1, I have to plug that in here to get, well, if I plug in, sorry, you can't see that very well. Apologies. Maybe this piece is properly here. Sorry. F of 0.5, 1 is 0.5 plus 1 minus 1, which is 0.5. And a half times a half is a quarter. So we get 1 plus a quarter, which is 1.25. We're moving up. So now our next step from 0.5 to 1 moves us up a little bit. All right, let's keep going. We're almost done. Well, we're halfway there, which is almost done. The next one, y of 1.5, is going to be y of 1 plus, again, a half times f of, here's where things are getting a little bit dicey. The new x value is 1. The new y value is the old y value, 1.25. Let me see something. I feel like no, that's fine. Yeah. So then y of 1 is just the previous value I had here, 1.25 times plus 0.5. F of 1, 1.25 is going to be 1 plus 1.25 minus 1, which is 1.25. So you get 1 1/4 plus a half of 1 1/4, which is something. It is something. That's going to be 0.625. Yeah, 0.625. So that plus that is 1.87. 1.875. Yeah. All right, we're almost there. Is it exciting? Yes, to me. So now we're like right about there. And then finally, okay, we do it one more time. Y of 2 is going to be y of the previous y value. Sorry, y of not the previous y value, y of the next step. So just to kind of see the pattern here, each time here, we're just adding h in there. Same deal here, right? We're just adding h, adding h, adding h. Whatever your step size is, that's what the x value is increasing by every step. So we're going to have plus 0.5 times f of 1.5 comma 1.875. And then we're going to get, so y of 1.5 is just the previous y value, 1.875 plus 1/2 times, all right, f of 1.5 comma 1.875 is just going to be 1.5 plus 1.875 minus 1, which is something gross that I calculated ahead of time and now I've lost my notes. No, it's right there. It's 2.375. If you multiply that by that and add that to that, you end up getting 3.0625. Cool. So we go over here. Oh, you can see that. And we try to fit everything on the screen at once. And we say, okay, well, we go up to 2 and about 3. So that's kind of the idea there is we're using that to estimate y of 2. And if you look, what's kind of actually nice here is that this differential equation is one of the differential equations that was on this handout that I gave you all before. It's number 4. So if you look back here for a second, what we really actually done, and you can't quite see this super well, but let me zoom in a bit here, is we've started at y of 0 equal to 1, and then we've kind of traversed this path where we've gone over and then up and then up and then up to get to about 3 point something. Kind of neat. Do we have enough time? Never. Do we have enough time to solve the differential equation? Maybe. Let's 3 minutes is kind of dicey. You are welcome to leave whenever you want. I want to show you the solution just because I think it's worthwhile. So you don't have to write this down. Let's take a look at our differential equation here. This is definitely not separable. Again, the x plus y here is problematic. So we're going to write this as y prime. I'm going to write it really obviously as plus -1 times y equal to x minus 1. Just to make it really, really obvious that p of x is -1. So p of x is -1, q of x is x minus 1. So our integrating factor is e to the integral of -1, which is e to the negative x. Multiply the whole thing by our integrating factor, and we're going to get e to the negative x times y prime plus e to the negative x times -1 times y equal to e to the negative x times x minus 1. And of course, just like every other time, this left-hand side is the derivative of the product. Integrating factor times y. Always, right? It is literally always whatever your integrating factor was times y, the derivative of the product of that. Every single time if you're doing integrating factors. Equals, sure, let's multiply this out. It's x e to the negative x minus e to the negative x. Integrate both sides. E to the negative x times y equal to x e to the negative x minus e to the negative x. Integral of that. And then you have to use integration by parts. Okay, fine. So we're going to get y equal to 1 over e to the negative x, which is e to the x, times the integral of x e to the negative x minus e to the negative x dx. And sure, we'll do it real fast here. Yeah, I got a minute. I'm going to think of this as x minus 1 times e to the negative x. So my u is x minus 1, my du is dx, my dv is the rest, which is e to the negative x dx. My v is negative e to the negative x. So I can, whoops, my battery is running low. No. Yeah, we'll just finish this real quick right here. So this is going to equal, sorry, times uv x minus 1 times negative e to the negative x minus the integral of v du, which is minus e to the minus x dx. And then if we add here, we get y equal to e to the x times x minus 1 times negative e to the negative x plus negative e to the negative x plus c. And then you'd have to plug in the 0, 1 to find your critical point or to find your constant. So you plug in x equals 0 and y equals 1, solve for c. And then after you do that, you can then plug in x equal to 2 to find the y value. And it should be reasonably close to what we estimated it to be, which is 3.06, whatever.